Hello everyone, and for this video um, we're going to talk about or discuss about the major topic, which is entitled Turing Machines and Computability, which will be presented by yours truly, Stephen Balo and Ma'am Asombrado. Now, before we begin, let me present to you top outline of topics for this major lesson or topic. So first, we have here the generalities on computability, and then also models of computation, followed by the Turing machines. What are Turing machines? And then we have here computable languages and enumerators. Next, we have Turing machine construction techniques, as well as Turing machine extensions and restrictions. And then last but not the least, we'll have the random access memory programs, its flowchart in sequential form. Okay, now we have here a video, if YouTube video. Now I won't be playing this video since uh, it would take the video much longer. No. So if you want to check, the video is right on YouTube. So the title of the video is Turing Machines, the Accidental Birth of Computer Science. There's some important this basically as this video basically summarizes the how the Turing machine was the computer science was born, simply by the discovery of the concept of Turing machines, which was conceptualized by Alan Turing. Okay, and it's also worth noting the just to call out the major highlight of this video. This was mentioned here about the Turing, a church Turing thesis, which was mentioned here also in the video. So again, if you want to check the contents of this video, watch it on YouTube. Yeah. Okay, so moving on to the next topic, we have here about model computation. So a model of computation is a model which describes how an output of a mathematical function is computed given an input. Now, we may not know, no, or we may not be aware, no, in our previous topics and lessons, but we already have encountered some examples of models of computation, and these are the following. Oops, sorry. So we have here finite state machines and push automata. We already encountered these. Uh, these are some examples of models of computation. And then we also have here some new models of computation. We have post systems, the writing systems, recursive functions, and lambda calculus, as well as logic gates and digital circuits. Then, of course, the random access machine and the Turing machine are also belong to the models of computation. Now, this list right here is not really the full list of models of computation, but these are just some of the worth noting. And yeah, now it's also worth noting this Turing machine here. This Turing machine is what we call the general model of computation. So yeah, the Turing machine is believed to be the most general computation model. Although though there are other models right here, like the, for example, this post system, writing system, and the lambda calculus. In terms of computing, they are just the same, the Turing machine. Okay. Anyway, I'll be mentioning it in this next bullet right here. So, despite many attempts, no computational model has yet been introduced that can perform computations impossible on a Turing machine. So, this is not a statement about efficiency. No? Other machines, notably the random access machine, can do the same computations with the Turing machine with either with more quickly or with less memory. But so instead, this statement here is about the feasibility of computational tasks. So if a task can be done on a Turing machine, it is considered feasible. If it cannot be done by a Turing machine, so that task is considered as infeasible. So that is why the Turing machine is a litmus test for computational feasibility. Okay. So next, we have here the standard Turing machine model. So the major components of a standard Turing machine model, as well as other variations of the Turing machine, is we have here the control unit, and then next we have here the what we call as the tape, and also we have here the read and write head, also called tape head. Now, so notice here in the tape, no, our tape initially, if it doesn't have a symbol, or rather, if we don't, its initial symbol is what we call a blank symbol. So in many, in some, this blank symbol is represented with this symbol, although in some books it may differ. In fact, later on I'll be citing another different variation of a blank symbol. Oh yeah, initially all cells of tape are initialized as blank symbol, and then also worth noting is the tape is infinite in capacity. So therefore, this tape can extend infinitely to the right as well as to the left side. Okay. Now, the control unit, no, uh, reads the symbols under the head and makes a straight state transition, the result of which is to either write a new symbol, no, or replace the current symbol, or and then change the state of the control, and then last is the head will move to the left if possible or to the right. Okay. So the reason right here, there's a parenthesis right here, if possible. That is because if the head is already at the leftmost portion of its tape, where, or rather, if the head is already at the leftmost symbol of our string that's been placed on the cells of the tape. So if we're going to move to the left, so it will not move. It's not supposed to not to move. That is why if in some cases we add a special symbol beside this beside the leftmost symbol of our string right here. Okay, indicating that just to aid our which will also be the guide of our control. Once the control unit uh, is able to read that symbol right here, the special symbol which will be inserted on the left of this, so it will not uh, move the head further to the left. Yeah. Okay, so we have here the formal definition of a Turing machine. So a Turing machine is defined as a 7-tuple. So in the Turing machine, we have here the following: the internal states, the input alphabet, and we have here also the tape alphabet, and also we have here the transition function, and then we we have here the blank symbol. So I already mentioned it a while ago that the blank symbol kind of depends on what the author depends on the authors of the book. So in this case, I've used a single book where the author has used this square to represent the blank symbol. But yeah, it depends. This is also common to other references, other authors. They use this one as to represent the blank symbol. Yeah, but for this, for my part, no, I will be using this one as the blank symbol, or it may from time to time I may interchange it with this one. And so anyway, going back, we have here the Q sub 0, which is normally the initial state. Yeah, and then we have here the set of final states. So yeah, Turing machine is defined as a 7-tuple. Now, a side note, no, again, it depends on the authors of the book that you are referencing. This may not be 7-tuple in other references and other books. It may be 5-tuple or it may be 6-tuple. But for the entire discussion, we will go with this one. This definition of the Turing machine as a 7-tuple. So in the definition of a Turing machine, we assume that the input alphabet is basically a subset of the tape alphabet, not including the blank symbol. And the transition function is defined as the following. So basically in the transition function, we have the following arguments, parameters. We have the current state and the current symbol being read by our head. So the result of that transition function would be a state. Could be the same state or perhaps a new state. And also here could it this we have here a tape symbol which would replace the current symbol being read, or in some cases the current symbol will not be replaced. So if we will encounter a symbol here and a symbol here, if they are just the same, so it means that there's no change in the current symbol. It was not replaced. But and then also we have here the move symbols L and R. L to represent that the head will move to the left. R to represent that the head will move to the right. So here is a visual representation of the following state transition. So for example, we have here the following the tape of our Turing machine, and its contents are ABC, and the head is pointing or is reading the A, and our internal state is Q sub 0. So according here to our defined transition function, on Q sub 0, input A or tape symbol A, it would result to a change of state Q1, and the A will be replaced by D. Also, the head will move to the right. So here is the visual representation of that state transition. Okay. So as always, the automaton starts in the given initial state with some information on the tape. Automaton referring to the Turing machine. Okay. So it then goes to a sequence of steps controlled by the transition function. So that is why we could say that the transition function is the heart of the Turing machine as it controls the sequence of steps of our Turing machine. So So during this process, the contents of any cell on the tape may be examined and read, no, and changed many times. Eventually, the whole process may terminate. Okay, take note, it may terminate. So later we'll know why. No? So which we achieve in a Turing machine by putting it into a halt state. Okay. So again, the Turing machine will terminate if we will put the Turing machine into a halt state. And when we say halt state, a Turing machine is said to halt whenever it reaches a configuration for which a certain transition, for which it's not defined in our transition function. Okay, so that is possible because our transition function is a partial function. In fact, we will assume that no transitions are defined for any final state. So the Turing machine will halt whenever it enters a final state. Okay, so we have here an example Turing machine right here. So its states are the following: Q sub 0 and Q sub 1, and its input alphabet contains the A and B symbols. Then our tape alphabet contains the A and B as well as the tape symbol, the blank symbol rather. And then we have the final state, Q's of 1, Q1. No. And also worth noting also is the definition of our transition function, where we have the list of transitions according to a certain state and symbol being read by our head. Okay, so according here, basically what's going on here is on Q sub 0 input on red currently reading the A symbol, it will result into Q sub 0 and B. So basically there's no change of state. However, our A symbol will be replaced by B, and then our head would would go to the right, one step to the right. And then in here, Q sub 0 in B symbol would result to Q sub 0 B. So there's no change of state and there's no change of the B symbol. B symbol will be as is, and then our head will move to the right. And then here, Q sub 0 blank symbol, it will go into a change of state. The result of that is a change of state. Q1 blank symbol remains the same symbol, and our head will move to the left. Okay, so to visually see what's going on in our Turing machine, we have the following example. No? So let's say that our Turing machine, or the tape of our Turing machine, contains the following string, input string AA, and of course our Turing machine initially will be at Q sub 0, and our head will point at the leftmost symbol of our input string. So yeah, according to our definition a while ago right here, so our Turing machine will be controlled by our transition function, whatever is defined in our transition function. So let's see. No, so first, no, our Turing machine, we're going to check, no, the current configuration. No, our current configuration, initial configuration is we have Q sub 0 state and our head reading the A symbol. So according here in our list of transitions, so on Q0A, our state will be QB and will be Q sub 0, and A will be replaced by B, and our head will move to the right. So that is why after this state transition, so this is the result of that. So this our Turing machine will be like this one. After this, one, our state transition of our transition function. So next, again, we'll just repeat the same. The Turing machine will just repeatedly check its list of transitions, and according here, we're currently at q sub 0 a. So again, our Turing machine will go into a state transition. The result of that would be this one. Okay, and then of course, our Turing machine will repeat again its steps. This is procedure, no, which it will given a q sub 0 and blank symbol, so it's defined right here. So according here, we will now have a state change, no, change of state. So q0 will now be q1, and our blank symbol will just be the same, and last, our head will move to the left. So that is why this one will result into this one. And yeah, since q1 on B symbol is not defined here, so therefore our Turing machine will now go into a halt state. Okay, so here is the transition graph, equivalent transition graph for this one, for our transition function right here. So for example, we have here this A, B, and R. This is basically the equivalent of this one. Okay, so according here, on q sub 0, A symbol being red, so A will be replaced by B, and our head will move to the right. Also, since this arrow points back to q sub 0, which means q of 0 will just remain q of 0. So that's what basically what's going on here, no? So also same here, same with this one, q sub 0, reading the blank symbol, it will just be replaced by this blank symbol, and our head will move to the left, and also our q sub 0 will now move to a new state, q sub 1. And also worth checking here that since q1 is our final state, so that's why we have here an inner circle to present that this is the final state. So yeah, it depends on you whether to just list down all the transitions, or if you want to visually represent it into our transition function, we like to create a transition graph. So yeah, depends. But on most books, they rely on just writing down all the transitions. Yeah. Okay, so next concept that I'm going to discuss is what we call here the instantaneous description, or it's also called as configuration. Okay. So as a Turing machine computes, changes occur in the current state, current tape contents, and current head location. Okay. So a setting of these three items is called instantaneous description or configuration of a Turing machine. So the reason that we need to understand this concept is because, let's say for example, we want to, this one right here, this first figure right here, rather than visually representing the current configuration of our Turing machine, we could write this into we could
translate this one into a written form, which is much more convenient in most cases. So how do we convert this visual figure of our current of the configuration of our Turing machine into a written form? So this is how we do it. No? We write it now. So we have here the configuration is written as a string of the form x1 q x2. This q right here could be q0, q1, q2, or so on and so forth. The x1 here represents the contents, the tape contents from A1, A2 up to a k minus 1. Now k2 represents the contents, the tape contents from the cells AK up to the AN. So basically what's going on is also sorry worth also noting that our we have here at internal state Q, and our head is pointing at AK. So this is also how we're going to write it down. No. So basically what's going on is the symbols A1 up to until AN show the tape contents, while the Q defines the state of the control unit here. Okay. This convention is chosen so that the position of the read-write head is over the cell containing the symbol immediately following Q. So the reason why Q here is inserted, our internal state Q is inserted beside this AK, it's because our head is pointing or reading, currently reading the AK. So basically, yun nga, just to recap our configuration, and our configuration is consist of the following: the current state, the current tape contents, the current head location. So if you want to write down the current state, so you just write here Q0, Q1, Q2. The current tape contents, you just list it down, A1, A2, AK, so on and so forth. And the current head location, in order to write it down, you just position the Q beside the symbol that is being currently read by our tape head. So that is why Q is beside the AK. Okay. So this notation may not be confusing to you, but anyway, we have an example. So let's say, for example, our configurations in the previous examples. If we're going to write it into its configuration in the written form, so for example, this first figure, this is how we write it down in in written form. So again, we have the tape contents AA. Just write it down, and then our Q sub 0, we just write it down here. And as you notice, Q0 is at the left of this A, this first A symbol. It's because our our tape head is currently reading the A. Yeah. Now for this figure right here, we have the following Q sub 0 state. Then our head is reading the A symbol, and our tape contents are the following: BA. So that is why if we're going to write it into a written form, so this is it, BA. And then as you notice now, Q0 is in the middle of the B and A symbol. It's because our head is pointing or reading the A. So that is why we put the Q0 beside the A symbol. So in this case, we now have here the blank symbol. included in our written form of our configuration of the Turing machine. That is because our head is currently reading a blank symbol. So that is why we put the Q0 beside the blank symbol. Okay. So next concept that we're going to discuss is the move. So when we say a move, okay, a move from one configuration to another will be denoted by this rotated T symbol. So basically, in a move, it just consists of a pair of configurations. The left configuration represents the current configuration, and then the right side represents the configuration after the move. So in this case, we have here in the current configuration here, we have the following tape contents ABCD. Our state is Q1, and our rated write head is on the C. So that is why this is the written form of our configuration. And as you notice, we have here this symbol, the move symbol, which means after this configuration, it will now move into this configuration. Okay, that is because of this what was defined by our transition function. So according here on Q1, C, Q1 will change into Q2, and our C will be replaced by E, and our head will move to the right. So that is why this is now the new configuration. Or if we're going to interpret this one, after this state transition, our current configuration will now change into this one. So as you notice, our C has now changed into E, our Q1 has now changed to Q2, and our state is now beside the symbol, which means that our head is now reading the D symbol. Okay, so here is another example. So same figure, no, and let's say for example we're going to write the series of moves, no. So let's say for example this is the initial configuration, and then our Turing machine move into this configuration, and then this configuration move to this configuration, and then lastly this configuration move into this configuration. So this is how we're going to write it down into its written form. So QA will move into this configuration, this one move into this configuration, and this one moves into this configuration. Okay, and also if you're not concerned with the configurations or the moves that was happening in the middle, no? You're only concerned with the initial configuration and the last configuration, so you can write it down into this form. So this time in this form, in this way of writing our moves, so we put our move symbol has this asterisk, and then we have here the initial configuration and then our last configuration, which means that our initial configuration A, after a arbitrary set of moves, it will lead into this configuration. Yeah, this is how you interpret this written form of our moves. Okay. So Turing machine M is said to halt starting from some configuration Q1 X QI X1 QI X2 if after a arbitrary set of moves, it will lead to this one. No, for any q, j, and a, for which are this one here is not defined in our transition function. So basically, what this means is if our after our arbitrary set of moves, once it reaches a certain configuration where this q, j, and a is not defined in our state transition, in our transition function rather, it will lead into a halt state. Okay, so the sequence of configurations leading to a halt state will be called a computation. So let's say, for example, going back here, let's say this we have. Let's say, for example, we have reached the halt state. No, so this entire set of moves is what we called also as a computation. This fourth sequence of moves from the initial state to the last configuration will where our Turing machine has been into a halt state. So yeah, this is what we call a computation. Also, this is also called a computation as well. Okay. So also worth noting, let's say for example we have your initial configuration, and let's say the machine goes into a loop because and it never halts. That is because it is possible for a Turing machine to never halt. So yeah, that's what I mean a while ago, that the Turing machine may halt. That is because it is possible for a Turing machine to go into a loop and never halts. Now, if you want to write it in a written form, so this is how you're going to do it. So basically, let's say for example, this is our initial configuration, and after an arbitrary set of moves, it just all leads to a loop state, a loop configuration. So yeah, this is how you're going to write it.
Okay, so next what we're going to talk about is Turing machine as language acceptors. So Turing machine can be viewed as a language acceptors in the following sense. A string W is written on the tape with blanks filling out the news portions. So basically ours, we have a string W, we put its symbols on the tape of our Turing machine. Okay. Then the machine is started in the initial state Q0 with the read write head positioned on the leftmost symbol of W. If after a sequence of moves the Turing machine enters a final state and halts, then W is considered to be accepted. Excuse me. So here's a formal definition of Turing machine as language acceptor. So let Turing machine M be the following. Okay, so here is the formal definition. Okay, let our language M be equal to this one. So when W or string W is not in the language of our machine, one or two things can happen. So the machine can halt in a non-final state, or it can enter in an infinite loop and never halt. So any string for which M does not halt is by definition not in the language of our machine. Okay, so here's a example where we're going to make a Turing machine as a language acceptor. So in this case, a problem is we're going to design a Turing machine that accepts the language denoted by the regular expression 00 clean kosher, which means the language accepts the following strings. A string, at least it accepts a string of two strings, or perhaps, or and also a string with 3 zeros, a string with 4 zeros, a string with 5 zeros, so on and so forth. However, it does not accept any string that contains a 1 in its symbols. So that is why it's also worth noting that the input alphabet is 0 and 1 as well. So to give you an idea on how we're going to create this, we're going to design our Turing machine. So here is a concept that I'd like to show you. So here is on the right side, we have here the Turing machine, and let's say this is the uh, our head. So starting at the left end of the input, we read each symbol and check that it is 0. So if it is a 0, we continue by moving to the right. Okay. If we reach a blank without encountering anything but 0, we terminate and accept the string. Okay. However, if the input contains a 1 anywhere, so let's say after a moving to the right until we reach a certain input that contains a 1 symbol, so we will halt in a non-final state, and therefore, since we halt the non-final state, this string will be rejected. Therefore, it's not part of the language. This string, in this example here, this 001 is not part of the language of that regular expression. So here's the solution. To keep track of the computation, two internal states, Q0 and Q1, and one final state is Q1 are sufficient. As transition function, we can take the following. So in Q0, input 0, the state remains the same, as well as the 0 will remain the same. However, we move the head to the right. And as for the state on Q0, and given an input which is currently read by a head as blank, so we will change into Q1 state. The blank symbol remains the same, and our head moves to the right. So to show you how visual example, and just to check if this is correct, if our solution really is correct, I have prepared a software where I just used a diagram. And if you are curious what program that I'm using, this is draw.io. It's free, and it's flexible because you can use it in creating flowcharts and even UML. So yeah. By the way, I've already prepared the Turing machine for this problem. And let's say, for example, oh sorry, I forgot. This should be Q0 because our initial state is Q0, and our head is pointing initially at the leftmost symbol of our string 000. Yeah. And so let us start. So our Turing machine will check if here, and based on our current configuration, we have Q0 and input 0. So according to our transition function of our control unit, so our Q0 will just remain Q0, and the 0 symbol will just remain 0. And however, we'll move this arrow or this head to the right. So yeah, and then we just repeat again. The Turing machine will again check if this one is in the configuration, if this configuration is has its corresponding transition. So yeah, it still has Q0 input 0, so same result. No changes in the Q0 and 0 symbol, and we'll just move this one to the right. Okay, and then yeah, repeat the same uh, result until such time we reach a certain uh, blank symbol on Q0. Now according here, it's suppose we are, I'm just going to move this arrow so that you can catch up with what is going on. So basically now we're at a configuration where our state is, current state is Q0, and the current symbol being read by our head is the blank symbol. So what happens here is our Q0 will change its state to Q1. This one just retains its symbol, and we move this one to the right. Okay. Now, if you're curious if on how if we're going to write all the configurations from start to scratch, so let's let's have a blank symbol right here, text, and so let's just go back to start. Okay. Oh, sorry. I'm sorry. It's not supposed to be here. Okay, wait, let me fix this. Okay, so where is that? Oh, I think I have to enter this one again. Should be left aligned. Okay, so Q0. Sorry. 0, 0. By the way, I'll just separate the Q0 in this 0 so that you will not be confused, because this is supposed to be a superscript, but just for the sake of saving time, we don't have to uh, or maybe we could, let's try if we could find a subscript right here. I don't think if we could, if there's a subscript. Okay, we do have a subscript pala. So let's try changing this one to subscript so that we will not be confused. Okay, so here it is. So our initial configuration is at Q0, and our head is pointing at the leftmost symbol, which is 0. So yeah, so after this transition, after transitioning, no, so we will be at uh, Q's of 0 uh, and 0 and right. So we'll move this one to the right. Okay, and this time we will write the move from Q0 from this initial configuration to the current configuration that we are having today. Oops. I think this is in subscript. This is weird. I guess I just have to write it in this form, since it's difficult to insert the reverse
the rotated T symbol. I'll just use this as a replacement. Okay. Anyway, we are now currently, it should change now into this one. Okay. So now we are currently at this configuration, and this is the written form of our configuration, a visual representation of our configuration right here, this one. So let's repeat again. We are at Q0, input 0. So according here, no changes in the state and symbol, and we just move to our head to the right. And yeah, and so this time our written configuration should look like this. Oops. Okay. So next, Q0, input 0. So yeah, we're just going to move again. As usual, no changes in the state and symbol. Now this time, this should be pointing up to a blank symbol. Okay, I guess I think what I did is I made this one into a subscript. Okay, so yeah, it's fixed. So as you can see now, I included the blank symbol this time because our head is currently pointing out the blank symbol. Okay, so I guess this will be the last configuration. So on Q0, input blank symbol, just this one. So what happens is we'll have a change of state, Q1, and then no changes in the input and the symbol, and we move our head to the right. And so this one should be moved here, and we add another blank symbol. Okay, so yeah, now since Q1 on blank symbol is not defined in our state, in our transition function, so our Turing machine is already has entered the halt state. So since we are at a halt state, and therefore, and also we halted as we as the Turing machine halted, no, went into a halt state, and its current state is in a final state Q1. So therefore, this is accepted. Okay, so let's try another string. So let's say 0, 1, 0. So and let's put everything back to the normal. I'll just copy this one, and I'll just put this of 0. Oops, sorry. Okay.
Okay, so let us start again from scratch, and this time we'll see how our Turing machine works visually, no, on a certain string 010. So Q0 input 0, so no changes in the state, and 0 remains as is. We move to the right. Our head moves to the right. So of course after that, I'll just copy this one just to make things faster. Oops, sorry. Okay. So now we're at a our current configuration is this one. Oh, sorry. This is supposed to be 01. Pala. 01, yeah. Yeah, okay. Okay. Now, let's see now. Q0 input 1. However, it's not defined here in our transition function. It doesn't have a corresponding transition defined here. So, therefore, our Turing machine goes into a halt state, and unfortunately, we halted we halt as our Turing machine halts. Our current state is not a non-final state. Q0 is not final state, so therefore this string 010 is rejected, or is rather not accepted in a language. Okay. So it's also worth noting that our move our move sequence of moves is only up to this one. Okay, so going back to our solution. So yeah, we only need two states for this for our Turing machine, and Q0 as the initial state, and Q1 as our final state. And as for our transition function, so this is how we're going to what's defined in our transition function. So as long as a 0 appears under red the read write head, the head will move to the right. If at any time a 1 is read, the machine will halt in a non-final state Q0, since Q0 input 1 is not defined here. Okay. So moving on to the next example here. This time we're going to design a Turing machine that accepts this language. So I think you're already familiar with this type of language. So basically, our language accepts strings AB, at least AB, or two A's and two B's, and also three A's, three consecutive A's, and followed by three consecutive B's, and yeah, so on, so on and so forth. So here's a visual idea on how we're going to create our Turing machine. So starting at the leftmost A, we check it off by replacing it with some symbol, let's say X. So upon reading, if our head encounters an A at the leftmost A, so we change it to X. Then we move our head. Our head moves to the right until such point that it finds the leftmost B. So which in turn is checked off by replacing it with another symbol. Let's say Y. Okay. Now it doesn't. You can actually have a different uh, symbol to replace the A's and B's, but what matters is there's uh, A and B have a different letter replacements. So it's up to you if you want A will be replaced by another letter, let's say perhaps D, or B should be E, or perhaps you could change this A to 1 and B into a 2 symbol. It's up to you. But that base but this is the basic idea. Okay? So again, just going back just to clarify things. So starting at the leftmost A, we check it off by replacing it with some symbol, let's say X. Okay, and then our head moves. Uh, it actually ignores the other A's. Let's say if we have two or more A's here, it just ignores. It just goes. Our head just moves to the right until it reaches the leftmost B. So which in turn is replaced by a Y. And then after that, we go left again. So as you notice, our arrow has moved to the right. Okay, and until such time that it reaches the leftmost A, and it will replace that leftmost A again with an X. Then after that, our head moves again to the right until it reaches the leftmost B and replace it with Y, and so on and so forth. So if we still have A in here, so of course this one will go back again to the right. And if after that, if there's another B, our head will move again. Oh, sorry. Once we have an A here, let's say we still have another A here and we still have another B here. So this one should move to the left. And then after changing that A to X, it will move again to the right to change the B. Until, traveling back and forth. This way, we match each A with corresponding B. And after some time, no A's and B's remain. So let's say all A's and B's have been replaced into their corresponding replacements. So yeah, the string must be in that language. So here's the solution for our Turing machine, or rather, this is how we're going to create our Turing machine. We will need the 5 states, Q0 being the initial state and Q4 as our final state. And then we have the following input symbols or in our input alphabet. So basically, our inputs are consisting of symbols. Our input strings has the following symbols only, A and B. However, in our tape symbols, we have included X and Y as well as the blank symbol. Now as for the transition function, so here it is. Now I won't be interpreting everything. You just have to anyway, we'll be moving on to our diagram. I already have prepared uh, the diagram for for the diagram for our second example, just to show you just test also if this is correct. So we'll see. So I already prepared the tape for our Turing machine. Has initialized its tapes. Uh, our and let's say we have the following input string A B B, and of course our control unit is at current initial state Q0. So let us start. Q0 input A. What happens is our state changes to Q1, and then we replace A with X, and then we move the arrow or the head to the right. Okay, so now we're at configuration Q1 input A. So here it is. Sorry. I just move this arrow so that you will be guided on with what transition I am referring to. So Q1 input A, what happens is there's no change in state and symbol. However, we just move the head to the right, or our head moves to the right. Okay, so we're now at Q1 input B. So according here, Q1 input B. Now we change our state to Q2, and we change the B into Y. Also, we move our arrow or head to the left. So yeah. Okay, so now we're at Q2 input A. So it's right here. Q2 input A. No changes in the state and symbol. So however, we move this arrow or this sorry if I interchange arrow and head because this one is an arrow obviously, but this is just a representation of our tape head. Okay, so now we're at Q2 input X. So once we've reached such Q2 and input X, we go back to our Q0 state, and also we move to the right. So therefore, this would be the result of our state transition. Okay, so let us check Q0 A. So we change our state to Q1 and we replace this with X, and then we move this one back to the right. Yeah. Oops. Okay. Now Q1 Y. So it's according here. So we just ignore. We don't. Yeah, we could say that we ignored this one because we didn't practically change the Y symbol here, and also our state goes the same Q1, no? So instead we'll just move the arrow to the right. Okay, and once it reaches the leftmost B, or the leftmost B. So where is that? Q1 B. Yeah, here. Okay. So we change Q1. Q1 was changed into Q2 state, and B will be replaced by Y. Also, we move the arrow to the left, or the head to the left. Okay, so we have Q2 input Y. So we just move this head to the left. Okay, then Q2 X. So we change state from Q2 back to Q0, and then no changes here in our symbol. However, we move to the right, so it should be around here. Yeah. And then we're now at Q0 Y. So we change into Q3 state, and then Y will be just the same. and then we move to the right. So we're now at Q3 Y, and according here, no change of state, and Y remains the same. However, we move the head to the right, and yeah. So now we're at Q3 blank symbol. So according here, Q3 blank symbol, Q3 will change to Q4, and the arrow, the blank symbol remains the same, and it should move to the right. Now, since I don't have a tape cell here, and we just add another one, because yeah, a tape is infinite in capacity. So this should be the final configuration now. Now, since we're at the final state, Q4, and then on input and blank symbol, since it's not defined here, since it's not defined here in our transition function, so the Turing machine goes into halt state, and since we halted at a final state Q4, therefore our AABB input string is accepted in the language. Okay, so you can check this one so that we don't have I'm not going to attempt to have another example for in rejected string. You just experiment this on your own so that this video will not take long. No, but if you are curious of, wait a minute, okay, of the computation, the written computation of our input for first particular input AABB. So here it is. So you might as well check it upon try experimenting on your own. So yeah. So at this point, the Turing machine halts in the final state so that string AABB is accepted. Yeah. Okay. So next, let's talk about Turing machine as transducers. So Turing machines are not only interesting as language acceptors, they also provide us with a simple abstract model for digital computers in general. Since the primary purpose of a computer is to transform input into output, so Turing machine acts also as a transducer. Okay. So the input for a computation will be all the non-blank symbols on the tape at the initial time. So at the conclusion of the computation, the output will be whatever is then on the tape. Okay. So again, the output of the computation will be whatever is then the contents of our tape. So thus we can view Turing machine transducer M as an implementation of a function f defined by the following. So w hat w is basically a result of our function f with the following input and w as the input. So provided that on q0 w, after an arbitrary set of moves, it leads to a final state, and then our contents of our string is now changed for some final state qf. So anyway, a function f with domain d is said to be Turing computable, or just computable if there is exists some Turing machine such that on this certain configuration Q0, and we have a certain string W after a set of arbitrary set of moves, it leads to a final state and function of the function with the input W. So yeah, so for all W, which is an element of the domain. So anyway, if that definition didn't make sense to, or is a bit confusing, we'll have an example for that. Okay, so given two positive integers, x and y, so design a Turing machine that computes x plus y. So yeah. So basically, a Turing machine that uh, computes the addition of two integers. Okay, so how are we going to do that? So we first have to choose some convention for representing positive integers. Okay, so for simplicity, we will use the unary notation in which any positive integer is represented by this one. Okay, such that the length of our unary notation is equals to the value of the x. Okay, so for example, number 3, no, so we will have a 3 once, no? So also, if for example we have 5 as our positive integer, its unary notation would be 5 once, 5 consecutive ones. So next, we must also decide how x and y are placed on the tape initially, and how their sum is to appear at the end of the computation. So that's another concern that we need to figure out. So we will assume that the unary notation of the x and the unary notation of the y are on the tape in unary notation, separated by a single 0, with the read write head on the leftmost symbol of this one. Okay. So after the computation will be on the tape, followed by after the computation W plus x plus y will be on the tape, followed by a single 0, and the read and write head will be positioned at the left end of the result. So if this explanation doesn't make sense, we have a visual example for that. So in this example, we are attempting to add 3 and 2, so 3 plus 2. So as you notice here in our uh, initial contents of our tape, so our tape contains the following: 3 consecutive ones. So this is the unary notation of the 3. Then, as mentioned, they are separated by this 0. No? So this 0 is followed by two consecutive ones to represent as the unary notation of the 2. So given the following contents of our tape, our goal is we simply move this 0 to the rightmost cell. So basically what happens is we now have 5 consecutive ones, and then the last symbol should be 0. So this is our goal. How do we move this one from here to here? So yeah. Okay, so all we need to do is to move the separating zeros to the right end of
of the W unary notation of our Y number, so that the addition amounts to nothing more than the coalescing of the two strings. So yan, I already explained it. Medyo nauna na ako ma-explain nito. Okay, so how do we translate that into a Turing machine? So to achieve this, we construct the following. So here is our set of states. So basically we have 5 states, and as usual, Q0 as our initial state and Q4 is our final state, and this will be our transition function. Okay, so once again, we'll be moving to the um, diagram that I prepared. Okay, so let me just zoom this so that you can see clear. Okay, so where are we? Okay, so I already prepared the tape contents. So this is, by the way, a 3 plus 2. Okay, just to let me just gonna add a label so that you will not be confused. Okay, so what we are trying to achieve here is 3 plus 2. So that, again, our 3 is represented as 3 consecutive ones, and then our 2 is represented as 2 consecutive ones, and they are separated by 0. Okay, so again, our goal is to move this 0 to the end. Okay, and it should be 5 consecutive ones followed by 0. Okay, so let's simulate this, no, to test if this solution is correct. So once again, I'll be using this arrow so that you can catch up to the what I'm trying to explain here. Anyway, let's start by, we have Q0 input 1. So according here, we just move this our head to the right, and no changes in the state. Okay, so same result. We move again. And then moved again. Oops, I think there's just correction. Okay, so now we have reached a certain configuration where we're at Q0 input 0. So according here, input 0 at Q0 input 0, we now change into a Q1 state, and we replace this 0 with a 1. Sorry. And then we move this one, our head, to the right. So now we're at Q1 input 1, and according here, there's no change in state. Q1 will remain the same. 1 symbol will just remain as 1, and we move once again to the right. So I guess we're at this Q1 and 1. So I guess the same result, no? Just move to the right. Okay, so now we have reached configuration where our current state is Q1, and the symbol that currently read by our head is the blank symbol. So according here in our transition function, Q1 blank symbol will result to a change of state Q2, and no change in the blank symbol. However, we move this one to the left. Okay, and then now we're at Q2 input 1, so we change to Q3, and then also we change this one now into 0. Also, we move this one to the left. Our head now moves to the left, and now we're at Q3 input 1, so we move again to the left. Okay, so I guess we're still at Q3 1, so I'll just repeat this step. Okay, and then move. Okay. Oops. And then until we move again. Now take note, we're now at the last one. So according here, just to repeat lang, Q3 input 1, no changes in the state, and no changes in the symbol. We just move to the left. So therefore now our state now, our head now points to a blank symbol, and we're at Q3 now. Now according here, Q3 blank symbol, we change into a final state Q4. No change in the symbol, however we move this one back to the right side. And yeah, so just to check, no, Q4 input 1, it's not defined here. So as you notice, there's actually a pattern, no. We normally don't define the corresponding transition for a final state, because once we reach a final state, our Turing machine should be in halt state na. Okay, so since this is not defined here in our state, in our transition function here, so therefore we have our Turing machine goes into a halt state, and since Q4 is yeah, now this time we don't ayun nga, we're in the final state, and as you notice, this is now the result of our computation 3 plus 2. So going back to what was discussed a while ago, let me just okay, so going back to here. Okay, so at the conclusion of the computation, the output will be whatever is done on the tape. So yeah, whatever was the contents of our tape a while ago, therefore that is the output of our Turing machine. Okay, so therefore the answer that is the final answer for our Turing machine. Yeah. So if you are curious of the configuration or the sequence of instantaneous descriptions for adding 3 to 2, so here it is. Okay. Yeah. Okay, so we have the last step and last example for Turing machine as a transducer. So this time, we're going to design a Turing machine that copies the strings of ones. So more precisely, we find a machine that performs the computation Q0, W. After a set of arbitrary moves, we reach a final state, and our contents of our tape head is WW. Okay. Okay, so let's I'll show you how we're going to figure this one out, how to create a Turing machine for this one. So to solve the problem, we implement the following iterative process. So let's say this is our W11, and what the first step would be replace everyone by an X. So replace this one. Okay. So find the rightmost X and replace it with 1. So since this is the rightmost, so replace it with 1. Okay. And then traveling to the right end of the current non-blank region and create a 1 there. So since we are already also at the right end of a current non-blank region, so 1, and this tape cell here is a non-blank and it's at the right end. No? So we create a 1 there beside this one. So yun. And we just repeat this step 2 and 3 until there are no more X. So again, we just go back to the start and replace, finding the rightmost X and replace it with 1. And yeah. Okay, so here is the solution for our problem. Okay. So this is the transition graph for our transition function, and as you notice, we only need 4 states. No? Q0 as the initial state and Q3 as the final state. So we could verify if this is correct. No? So let's say, for example, we have the computation for the string 1 1. So this is the current computation Q0 1 1, and yeah, after you can check this on your own if this is correct, but yeah, this should be, if you're going to trace it on your own, it should be the same as this example right here. So yeah, 1 1 is our initial contents of our tape, and after a set of moves, we've now reached to a configuration where we're at Q3, and now our string 1 1 has been resolved to this one. We have now 4 ones. Okay. So let's say, for example, if this would be 3 ones, so our tape at the end of our computation, it should be now 6 ones. Okay. Okay. So let's talk about our next topic, which is about computable languages. So I would like to emphasize this word computable. So its synonyms is recursive and decidable. So the reason I need to highlight this was because this term changes depends on the book or author that you are looking at, no, you are reading at if you are reading a book. So anyway, a language L is called computable or recursive, decidable. So recursive language, decidable language, computable. They're just the same. Okay. So again, language L is computable if there's a Turing machine that, when presented with any uh, input string, it halts and accepts if the string is in the language, and halts and rejects otherwise. So again, take note: a language is computable, recursive, or decidable if there's a Turing machine that, when presented with any uh, finite input string, it will either halt and accepts the string if the string is in the language, or halts and rejects. So here's a visual representation of a Turing machine, okay, that accepts a certain given a certain input. It either halts and rejects the input, or it halts and accepts the input. Yeah. Now, here are some computable languages right here. So we have here regular languages, which are the language that is accepted by a finite automaton. Okay. So according here, regular languages are recursive because you can make a Turing machine equivalent to a finite automaton by not using a tape. But basically, what it means is it's just like the same as what we did in our first example with the language acceptor, the regular expression 00 clean kosher. So what our automaton or Turing machine did was it just reads the tape contents, and it didn't make any changes, no, to the contents of the tape. Also, context-free languages are also recursive or computable, no, because you can make a Turing machine equivalent to a pushdown automata by using a tape as a stack. No? So basically, uh, we treat the tape as a stack, no? Only reading and writing to the last non-blank symbol. Okay? So yeah. So therefore, regular languages which are accepted by uh, finite automaton, and context-free language which are accepted by pushdown automata, they are considered as computable languages because we can create an equivalent Turing machine for those languages. Okay, so next we have computably enumerable language. So a language L is computably enumerable or semi-decidable if there's a Turing machine that will halt and accept when presented with any string in the language as input, but no, may either halt and reject, or it will loop forever when presented with a string not in a language. So this is the difference between a computable language and a computably enumerable language. So in a computable language, it will always halt, and it will either be the string would either be accepted or rejected. However, in the case of language L, uh, it will be computably enumerable if there's a Turing machine that will halt and accept, or may not halt and reject, or it may loop forever when presented with a string with not in the language. So now let's talk about here these what we call enumerator. So some people use the term recursively enumerable language for Turing recognizable languages. That term originates from a type of Turing variant called an enumerable. By the way, Turing recognizable is Also what we call computably enumerable language. Okay, just to make this clear. So again, the enumerator, the name of the enumerator, it was derived from, it originated from, sorry, the term recursively enumerable language came from this, what we call enumerator. Okay. Now, what's the relation of the enumerator to the computably enumerable language? So we will find out, okay, in the next few slides. So uh, let us first understand what a enumerator does. So enumerator is just a Turing machine with an attached printer. Okay. So basically, we have this time our Turing machine now has not only a tape, no, a work tape. It also has this what we call printer, which could be a tape, yeah, which is also a tape. No? So the Turing machine can use that printer as an output device to print strings. Every time the Turing machine wants to add a string to the list, it sends the string to the printer. Okay. So an enumerator E starts with a blank input on its work tape. So basically, this work tape is everything here, all its cells are initialized as blank symbols. Okay. So if the enumerator doesn't halt, it may print an infinite list of strings. Okay. So the language enumerated by E is the collection of all the strings that it eventually prints out. Okay. And moreover, E may be generated and may generate the strings of the language in any order, possibly with repetitions. So there's a possibility that the strings here that will be printed by the printer will have some repetitions, and also in any order. So here's the formal definition of an enumerator. So it's defined as a 7-tuple, and where we have here Q as the finite non-empty set of states, and we have here the output or print alphabet, and we also have here the working tape alphabet, and we have the transition function. So and then we also have here the Q0 as the initial state or starting state. Q print will be the print state, and we also have here the reject state, such that the print state and reject state are not the same. Okay, so now let us answer the question: how is enumerator related to the computably enumerable language? So according to a theorem, a language is Turing recognizable or computably enumerable if and only if it can be enumerated by a enumerator or a Turing machine enumerator. So yeah. Okay, so that's it for my part. Then next topic will be discussed by my partner, Ma'am Asombrado. And yeah.
Okay, so for the continuation of our report, our goal is to give you a sense of how Turing machines can be used to compute in a manner not unlike that of a conventional computer. So eventually, we want to convince you that a TM is exactly as powerful as a conventional computer. So to make the ability of a TM clearer, we shall present a number of examples of how we might think of a tape and a finite control of a Turing machine. For the outline of my report, I'm going to discuss the TM construction techniques and the TM extensions and restrictions. So for the techniques for TMs, we have here, we can use the finite control of a TM to hold a finite amount of data in addition to the state, which represents a position in a TM program. So for the method, think of a state as Q, A, B, C. For example, when think of the finite control to hold three data elements A, B, and C. So see figure in the next page. We have here in the figure 8.13 contains the symbol X, Y, and Z. So like the technique of storage in the finite control, using multiple tracks does not extend what the Turing machine can do. So it is simply a way to view tape symbols and to imagine that they have a useful structure. So next is the extensions to the basic Turing machines. So in this section, we shall see certain computer models that are related to Turing machines and have the same language recognizing power as the basic model of a TM with which we have been working. So one of this is the multi-tape Turing machine, which is important because it is much easier to see how a multi-tape can simulate real computers or other kinds of Turing machines. So compared with the single tape model we have been studying, yet the extra tapes add no power to the model. So as far as the ability to accept language is concerned. We also then consider the non-deterministic Turing machine, which is an extension of the basic model that is allowed to make any of the finite state of choices of move in a given situation. So this extension also makes programming Turing machine easier in some circumstances, so but adds no language defining power to the basic model. So the above extensions make no increase of the original TM's power but make TMs easier to use. Like the multi-tape Turing machine, which is useful for simulating real computers, and the non-deterministic TM or Turing machines making TM programming easier. So we have here in the figure 8.16, which is a multi-tape TM, is suggested. So the device has a finite control state and some finite number of tapes. So each tape is divided into cells, and each cell can hold any symbol of the finite tape alphabet. So as in the single tape TM, the set of tape symbol includes a blank and has a subset called the input symbol, of which the blank is not a member. So the set of state includes an initial state and some accepting states. So initially, the input string is placed, or the input, which is a finite sequence of input symbols, is placed on the first tape, and the other tapes or all other cells of all the tapes hold the blanks. Next is the finite control is in its initial state, and the head of the first tape is at the left end of the input, and all other tape heads or the tape heads of other tapes are arbitrary positions. So all other tape heads are at some arbitrary cell, and since tapes other than the first tape are completely blank, it does not matter where the head is placed initially. So all cells of these tapes look the same. So a move uh, of a multi-tape TM depends on the state and the symbol scanned by each of the tape heads. So in one move, the multi-tape TM does the following. So first is the control enters a new state which could be the same as the previous state. On each tape, a new tape symbol is written on the cell scanned, and any of these symbols may be the same as the symbol previously there. Next is each of the tape heads makes a move which can be either left, right, or stationary. So the heads move independently. So different different heads may move in different directions and some may not move at all. Next is the running time and the many tapes to one construction. So let us now introduce a concept that will become quite important later. So the time complexity or running time of a Turing machine. We say that running time of the on input W is the number of steps that M makes before halting. So if M doesn't halt on W, then the running time of M on W is infinite. So the time complexity of TMM is the function T of n that is the maximum over all inputs. W of length n and of the running time of m on W. So we have here the argument that the running times of one tape and multi-tape TMs are within a square of each other is as follows. We have here in theorem 8.10 the time taken by the one tape TMN of theorem 8.9 to simulate n moves of the K tape TM is 0 O sub O of n raised to the power of 2, meaning the equivalence of the two types of DM is good in the sense that their running times are roughly the same within polynomial complexity. So next is the non-deterministic Turing machines. So a non-deterministic Turing machine has a multiple choices of next move. In essentials, a transition of qx is equal to q sub 1, y sub 1, e sub 1, q sub 2, y sub 2, d sub 2, to q sub k, y sub k, and d sub k. So a non-deterministic TM differs from the deterministic variety. So we have been studying by having a transition function such that for each state q and the tape x and the tape symbol x, which has a transition of q and x, is a set of triples, which is the q sub 1, y sub 1, d sub 1, q sub 2, y sub 2, d sub 2, q sub k, y sub k, and d sub k. So where k is any finite integer and the non-deterministic Turing machine can choose at each step any of the triples to be the next move, and it cannot, however, pick a state from one tape symbol from another. So and the direction from yet another. So the non-deterministic TM is not any powerful than a deterministic TM and is said by the following theorem. In Theorem 8.11, if M sub n is a non-deterministic Turing machine, then there is a deterministic Turing machine M sub d such that M sub L of M sub n is equal to L of M sub into a finite control of M sub d is the knowledge of what choices of moves of M sub n. So M sub n has for each state and symbol. So if the state in the current ID is accepting, then M sub d accepts and simulates M sub n no further. So however, if the state is not accepting and the state symbol combination has k moves, then deterministic is uses its second tape to copy the ID and then make um, make k copies of that ID at the end of the sequence of IDs on tape 1. So deterministic machine modifies each of those k IDs according to a different one of the k choices of move that non-deterministic machine has from its current ID. So a deterministic machine returns to the mark current ID and erases the mark and moves the mark to the next ID to the right. And the cycle then repeat with the step 1. So next is for the non-deterministic, again, for the non-deterministic TMs, the equivalent deterministic TM constructed for a non-deterministic TM in the last theorem may take exponentially more time than the DTM or deterministic Turing machine. So it is unknown whether or not this exponential slowdown is necessary. We also forbid this restricted TM to print a blank as the replacement tape symbol. So the value of these restrictions is that we can assume IDs consist of only non-blank symbols and that they always begin at the left end of the input. Here, for the we have allowed the tape head of a Turing machine to move either left or right from its initial position. It is only necessary that the TM head be allowed to move within the positions at and to the right of the initial head position. So in Theorem 8.12, with a Turing machine with semi-infinite tapes, in Theorem 8.12, it states that every language accepted by a TM M sub 2 is also accepted by a TM M sub 1 with the following restrictions. M sub 1's head never moved left of its initial position. And M sub 1, or so type is semi-infinite is essential. So M sub 1 never writes a blank. So in essential, M sub 1 and M sub 2 are equivalent. Stack alphabet, which it uses for all its stacks, and a move of the multi-stack machine is based on the state of the finite control in figure 8.20. But in a place of each stack is a counter. So counters hold any non-negative integer, but we can only distinguish between 0 and non-zero counters. That is, the move the counter machine depends on its state and magdepende sa iyang state, input symbol, and which if any of the counters are 0. So in one move, the counter machine can first change state, or a move conducts the following operations: changing the state or change state, and add or subtract 1 from a counter which cannot becomes negative. So add or subtract 1 from any of its counters independently, meaning um, from kung mag-add ka or mag-subtract 1 from any of its counters, it's independent or independently. So however, a counter is not allowed to become negative, so it cannot subtract 1 from a counter that is currently 0. So another way, or way 2, is as a restricted multi-stack machine, with each stack replaced by a counter implemented on a stack of a PDA. So a counter machine, so way 2, a counter machine may also be regarded as a restricted multitask machine. So the restrictions are follows. First, there are only two stack symbols, z sub 0 and x. So there are only two stack symbols, which we shall refer to as z sub 0, which is the bottom of a stack marker, and x. Next is z sub 0 is initially z sub 0 is the initial stack symbol, like that of a PDA. So therefore, z sub 0 is initially on each stack. Next, can replace z sub 0 only by z sub raised to the power of, by x raised to the power of I, z sub 0 for some I is greater than or equal to 0. So we may replace z sub 0 only by a string of the form x raised to the power of I, z sub 0 for some I is greater than or equal to 0. So next is, can replace x only by x raised to the power of I for some I is greater than or equal to 0. So we may replace x only by x to the power of I for some I is greater than or equal to 0. That is, z sub 0 appears only on the bottom of each stack, and all other stack symbols, if any, are x. Okay, so accepted by two stack machines. So we then need to show how to simulate a stack with counters. Um, I think that's all of my report. And for the continuation of our topic, Sir Stephen will continue about the random access machine programs. And
Okay, so I'll be explaining this last topic, which is about random access Turing machine. Now, despite the apparent power and versatility of the variants of the Turing machine, as well as the standard Turing machine we have discussed so far, so they all have a quite limiting common feature. That is, their memory is sequential. So, what I mean by sequential is, that is, in order to access the information stored at some location, the machine must first access one by one all locations between the current and the desired one. So, for example, if the the head is at the first cell and you want to access the last symbol of your input string, so you have to read the second cell, the second third cell, the the third tape cell, the fourth tape cell, so on and so forth, until you reach the last uh, cell that contains the last symbol of your string. So again, that's the common limiting, quite limiting common feature of all the Turing machines, as well as the variants Turing machine. their accessing of uh, the memory is sequential. Memory referring to the tape. Okay. So in contrast, real computers have random access memories. So each element of which can be accessed in a single step, okay, if appropriately addressed. So what would happen if we equip our machines with such a random access capability, enabling them to access any desired tape square in a single step? So to attain such capability, we must also equip our machines with registers capable of storing and manipulating the address of tape squares. Now, to visually show you what a random access Turing machine is, so this is what the register that I'm referring to, and we have here the usual uh, tape with the following tape cells, and then now we also have this what we call the program counter. Okay. Now, a random access Turing machine has a fixed number of registers. So in this diagram so far, it has only 4 registers, and a one-way infinite tape. So this time our tape doesn't have an infinite capacity to the left, so it just has a one-way one-way infinite tape to the right. Okay. And each register and each tape is capable of containing an arbitrary natural number. So in this, according to the reference that I used, so registers and the tapes only contain uh, natural numbers. So when we say natural numbers, that is start from 0, 1, 2, 3, 4, 5. Uh, Therefore, it doesn't allow contain negative numbers. So yeah. So notice also the special role of register 0. This one. It is the what we call the accumulator. Okay, where all arithmetic and logical computation takes place. So basically, the results of the arithmetic and logical computation, they are stored here in this register 0, which is also why it's called it has a special role as accumulator. Okay. Then we also have this what we call program. Okay, so this is but just an example program. No? It's kind of like similar to how we program computers, no, in high level programming language or in assembly language. So we have a set of instructions ranging from the one. So this one here, basically, this is the first instruction uh, to be executed by our Turing machine, random access Turing machine, followed by this one, and it doesn't necessarily execute this sequentially. It depends if it encounters a instruction that will allow us to jump to another instruction. Anyway, we'll be having an example for that later. No, so the machine acts on its tape squares and its registers as dictated by a fixed program. So this is the program, the analog of transition function of ordinary Turing machines. Okay. So the program of a random access Turing machine is a sequence of instructions of a kind reminiscent to the instruction set of a actual computer. Now here is this is what we call the instruction set of a random access machine. Now this may be different to other references, but for the sake of our discussion, this topic will be using this uh, instruction set. So again, it depends. Some random access Turing machine has a small instruction set. Some have more instruction set. But yeah,
again, we'll just use this reference that I took from reference. We'll be using this for to discuss the random access Turing machine. So, just to give you an idea how each instruction works. So, for example, this read 0. So, this read J. So, what happens is the value of the register 0 will be equal to the tape, uh, and the cell of the tape depends on what is the value of our rj. Okay. So if j is 2, so whatever is the value of r2, the value that is stored in the r2, that would be the tape cell that we're going to access, and the value of that tape will be assigned to r0. So write j, what happens is our tape on a certain cell, depending on the what's the value of the rj, would be equal to the register 0. And then stored j, rj, let's say this is 1, r1 would be equal to the value of the number that's stored in the register 0. So load j is the where am I? Load j is interpreted as the register 0 would be equal to the number of rj, or the value of rj. So load equals c, the register 0 r0 will be equal to whatever is the value of c. So if load equals 3, r0 would be equal to 3. Then we have add j, register 0 would be equal to it's the current value of register 0 plus the value of rj. Then add equals to c, register 0 would be equal to the current value of register 0 plus the value of whatever is the value of c. Okay. Then sub is basically subtract. Okay. Subtract j. So our register 0 would be equal to the r0 minus rj. So whatever the value of the rj, it is subtracted into r0, and the result of that, okay, it depends on, let's say for example, if the difference of this is a positive number, let's say 1 or 2 or 3, so that would be the value that we assign to r0. That is why this is what the max is for, kasi there could be a possibility that subtracting 0 and rj would result into a negative value. So if the difference between r0 and rj is negative, value 0 will be the value to be assigned with the register 0. It's because in this random access Turing machine where negative numbers are not allowed. Okay, so this is, so in here subtract equals c, so our register 0 would be equal to the difference between the r0 and the value of c. And again, as the same with our previous instruction, whoever between the values, the value of the difference here and 0, let's say if the difference of this is positive, so the result here would be the value assigned to register 0. But if the difference is a negative number, 0 will be assigned instead to register 0. Then we have half. Half is divide. No? So r0 would be equal to the
then the value of the R0 divided by 2. And also this is I guess ceiling or floor. I don't remember. I think this is ceiling or floor. I don't remember what's the mathematical kind of this. Anyway, we have jump S. So this is the instruction that is responsible for us to jump to from one instruction to another. No? So what happens is whatever is the value of x, so the value of our program counter, no, just to go back here, this one, the value of our program counter would be equal to the value of s, and then j pos. There's a certain condition. So this is the difference between this is the difference between the jump and the j pos. So this j pos, j0, these are just the same as the jump instruction. However, the difference is they have this condition. No? So in the j pos, if register 0 is greater than 0, so we execute this one instead. Okay, but if not, we just go on. We just increment. Okay, so in the J0, if the register 0 is equals to 0, so we execute this one. But if not, we just increment the program counter. And then last, we have the halt instruction. So what happens in the halt instruction is the program counter is set to 0. Okay. Okay. So it's also worth mentioning that all of these instructions here, increment the value of our program counter by 1. So let's say after executing this one, it will increment the program counter by 1. This one also, except for the jump instruction and the JPOS and however, in the JPOS and J0, if the condition is false, so it will just be a regular increment of the program counter. But in the jump, so there's no increment on the program counter, because what's going to happen is the value of the program counter will change depending on what's the value of the s here. Okay, so again, all instructions change the program counter. It will increment the program counter's value by 1, except for these jumps instructions. Okay, so it's also I would like to label the register number J, then the T here is the current content of the tape square, and C is any natural number, so 0, 1, 2, 3, and so on and so forth. Instruction number. So yeah. Okay, so here's the definition of the random access Turing machine. So a random access Turing machine is a pair M, so K, and this big pi symbol. So where K, small k, is equals to 0, greater than 0, which is the number of registers. So basically, if we're going to define the Turing machine, because again, a Turing machine, random access Turing machine has a fixed set of registers. So whatever you put here you specify here, let's say this is 5, so therefore we have 5 registers. So if the value here is 4, we have 4 registers, so on and so forth. And as for this one, this pi, the capital pi or big pi, so it contains basically this is the program, okay, which is a finite sequence of instructions where each instruction, small pi I, is of one of the types shown in the previous figure. So this one,
Okay, so basically our program I1 pi1 could contain either one of these. The pi2 could either one of these instructions. So yeah, so on and so forth. So basically, just to go back to our previous example, this one here could, an example of this one is this one. So our pi 1 is this one, pi 2, small pi 2 is this one, small pi 3, and this entire instruction set from small pi 1 to small pi 20, this is what the program or the capital pi. Okay, so we assume that the last instruction is always a halt instruction. Yes. Okay, so where are we? So in the registers, they hold, as already mentioned a while ago, they hold natural numbers, which means each register can only hold values ranging from 0 to positive infinity. And also here in our tape, each cell of our tape can only hold the natural numbers. So what else? In the program counter, it holds values from 0 to p. P is the highest instruction number. Halted configuration if k is 0. Yeah. And also worth noting, our registers initial value are 0, and as well as the tapes, their initial value is also 0. And as for the program counter, however, its initial value is 1. So here is how an execution of a random access machine proceeds. So first, initially the inputs are loaded in the first n cells of the tape. So, and then at each step of the execution, the random access machine executes the program line pointed to by the program counter. So this is where the program counter comes into use. So whatever is the current value of the program counter, the corresponding instruction on that number will the value of the program counter will be executed. Okay. Then after executing the instruction, the value of k is incremented by 1. So unless the instruction is jump, J0, JPause, and halt. So the only exception to this incrementing by 1 are these instructions jump, J0, JPause, and halt. But if the instruction is J0 or JPause and the condition is not satisfied, so the value of our program counter will only be incremented by 1. Okay. And last step, if the current instruction is halt and is executed, the random access machine halts. And so yeah. So by the way, the example that we provided a while ago, this is actually the program for multiplication, and we will simulate this one later on. No? So in a random Turing machine configuration, so this is for how we're going to write how are we going to make the written form of a Turing machine, RAM Turing machine configuration. Okay. So a configuration of a random access Turing machine is k plus 2 tuple. So basically, whatever is the value of whatever is the number of our registers plus 2, that would be the number of tuples for our configuration. So for example, if we have 5 here as 5 registers, so we have 7 tuples. So if we have 4 registers, we have 6 tuples. Okay. So it is also written in this format, no? K, capital K will be the current value of our program counter, R0, R1 until RK minus 1. These are the values of our register 0, register 1, so on and so forth, and the value of our last register. And then T is the tape contents. And the tape contents is just a finite set of pairs of positive integers. So that is a finite subset of um, natural numbers minus the zero integer. So basically, what's in the tape content is basically a set of pairs, and each pair um, could only be in a value of natural numbers without the one. So each pair is not allowed to have zero as their value. So okay, so going back to our example program here, multiplication, we're going to simulate this one shortly. No? So let me just exit this presentation. Okay, so here is the um, random access Turing machine that I've already prepared. It's already initialized. Oh, sorry, I forgot this one. This should be 0. So it's already initialized for the tape contents. Actually, we don't need the the tape for this multiplication program. Most of the time, we'll be only needing to use the registers only. Excuse me. Now we've already initialized the registers. 5, the register 0 is 5, and then our register 1 is 3. So the reason for that is we're trying to uh, figure out the value of, or the product of this 5 times 3, and we're going to do that using the random access machine, the Turing machine. Okay. And yeah, this is the instruction or the list of instructions that we need for a program in order to achieve this multiplication of any two positive integers. Now let us begin, no, by whatever is the, since the program counter is initially, its initial value is 1, so it is we'll start executing the first instruction here. So store 2. So when I say store 2, it means that the register 2 will be equal to the value of R2. So R2 will be equal to 5. So therefore, we change this one to 5. And after that, as I mentioned a while ago, that all instructions at the end of executing each instruction, the program counter will be incremented by 1. So therefore, sorry, 1 will be incremented by 1, so our program counter will now be 2, and therefore in the next instruction that we're going to execute will be 2. So now let's have here execute this load 1. So register 0 will be equal to register 1. So which means since the value of R1 is 3, so that would be the value that we will replace in our R0. And so we change this one, we increment 2 by 1. So now our next instruction we need to execute is instruction 3. So now we're at J019. So according here, if uh, we will only jump to 19, instruction number 19, if this is true, R0 is equal to 0. However, since our register 0 is 3, so we will only increment our program counter by 1. And therefore, we'll jump to instruction 4. So next, we have half. Now, I've already searched uh, what this means. So basically, this is a floor function. So what happens is the value of register 0 would be equal to the register 0, its current value of register 0, divided by 2, and you execute the floor function of the result of this division. So since we're the value of R0 is 3, so it should be 3 divided by 2. And the answer of that should be 1.5. Now, according to the floor function determines uh, the largest positive, no, not the largest integer that is less than the uh, value here. So since our current value is 1.5, and therefore the floor uh, after executing the floor function of the given value 1.5, the result would be 1. So therefore, we assign 1 to register 0. Okay. And therefore, we now we increment our program counter, and we will now execute instruction 5. So store 3, R3 would be equal to R0. So R0 is 1. So therefore, we change R3 to 1. Sorry, should be 1. Okay, and we increment this by 1. So we'll execute this instruction 6. Load 1, so register 0 is equals to R1. So the value of R1 is 3, so we change R0 to 3. And we increment our program counter by 1. So now we'll be executing the instruction 7. Wait, oops, sorry. Okay, so now we have here sub 3. So according here, it's R0 minus R3. Kasi according here, it's whatever is the value here should be the value, or should be substitute the value of J. So therefore, we are referring to R3. No? R0 minus R3, so 3 minus 1, so that is equals to 2. So therefore, that would be the value that we assign to R2. So R2 will now be equal to, or R0 will be equal to the value of 2. Okay. So again, 2 is the result of the subtraction between R0 and R3. Yeah, as specified here. And we assign that value to R0. So we increment 7 with 8, and then so we'll be executing instruction 8. So now we have same instruction. So R0 minus R3, so it's 2 minus 1. So the answer to that is 1. So therefore, we will assign that to the R0. Now, by the way, just to recall why we are assigning the value here, the answer of this the difference between here, no, instead of 0. So the only time that we will assign the value of 0 if the difference between these two registers is negative. So it's because we are not in this particular random access machine, it doesn't allow negative numbers to be assigned to the registers or to the tapes, tape cells. So yeah. Okay, so we're done with this. So we will be our program counter will be incremented now by 1. So we will now be executing the the instruction 9. So J0 13. So we're supposed to jump to 13 if this is true. However, since our 0 is equal to 1, so we'll just increment this one to 10, and therefore we'll be executing the instruction 10. So load 4, R0 would be equal to R4. So currently R4 is 0, so we change this R0 now to 4. And we increment again. So now we're going to execute the instruction 11. Add 2. So R0 plus R2. And the result of that, we'll assign it to R0. So add, where is that? R2 is 5. So 0 plus 5 is 5. So therefore, R0 will now be equal to 5. And then we proceed now to instruction 12. Store 4. So R4 will be equal to the value of R0. So R4 will be equal now to 5. And then we increment by 1, 13. Okay, so next, load 2. R0 is equals to R2. So R2 is equals to 5. So therefore, yeah, the value of R0 will still R5. So, and then we increment by, and then next we have instruction 14, add 2. R0 plus R2. So R0 is 5, R2 is 5. Therefore, if we add it together, we have the value of 10, and we assign the result to R2, R0 rather. Excuse me. And then we increment. Now we execute instruction 15. So store 2. R2 is equals to R0. R2 is 5. So we assign the 5 to R0. And then 16. Oh wait, I think I misinterpret. R2 would be equal to the value of R0 pala. So therefore I change this instead. Okay. Oh wait. Let me double check. Oh yeah, that's correct. So this would be 10. And then we increment. So okay, so where are we? Are at instruction 16. Load 3. So R0 is equals to R3. R3 is 1. So that would be the value of our R2. And then let's execute the store 1. So R1 would be equal to R0. So R1, R0 is currently 1. So we will change the R1 into 1. Okay, and everything. And so we jump to instruction 18. Should be here. Okay. So jump. I think this is an error by the author. I think this should not be here because it's supposed to be sequential. No? 1, 2, 3, 4, 5. After 17, it should be 18. So I guess this is an extra excess instruction that should not be here. No? Anyway, right now we are going to execute is jump 2. So which means k, which is the program counter, that value would be changed to 2. Therefore, program counter will change its value to 2. And so we will jump now to instruction 2. We'll go back to instruction 2 now. Okay. Now, I won't be finishing this entire um, tracing of the instruction here because it will take a while. No? Anyway, I will just show you the sequence of configurations of our Turing machine, a random access Turing machine. But you can try this on your own if you really are curious on how the configurations was derived. No? So yeah. Okay, so let us jump into the uh, sequence of configurations for our random access machine. No? So here's our next typical sequence of configurations. Now since this machine does not interact with the tape squares, so the T part of our configuration is empty. So therefore, as you can see here, we have this empty symbol, empty set symbol there, which means we don't have a set of pairs of tape squares. So what we only have in our configuration is, first we have the current value of our program counter, and then followed by the values of our register 0, register 1, register 3, our register 2, R3, and R4. Okay, so if you follow along the what I have demonstrated a while ago, so this should be the corresponding configurations of our RAM, no, or random access Turing machine. So we've reached up to here, up to this one. Okay, and so if we're going to continue further, so after a arbitrary set of moves of configuration, we will end up reaching this configuration where we're at program counter will be 18, and these are now the values of our registers. So after that, we will move to this configuration. So as you notice now, we change our program counter now is at 2, no, and this is the current uh, values of our register. And then after that configuration, we move to this configuration. Our program counter is 3, no? So if we're going to check 3, which is J019, so therefore we will jump at 19 if R is equal to 0. So since register R is equal to 0 right here now, so therefore we will jump into instruction 19. So that is why our program counter now is equals to 19, and so it will the value here at the instruction here at instruction 19 is load 4. So therefore we load the excuse me the value of r4 to r0. So that is why r4, this is the r4, and after that instruction, the load 4, it was executed, we will reach into this configuration where we are at the program. Our program counter is 20, and now our r0 value is now 15. Okay, and yeah, we have figured out, as I mentioned, on that r0 is the what we call the accumulator. So whatever is the result of the accumulator is will be the answer or the computation for our, or yeah, the result of our problem, no, which is multiplication. So therefore from the first configuration we have here 5 and 3, and then after is consecutive move of configurations, we finally reach this configuration where we were able to determine the result of the product of 5 and 3, which is 15, and it is stored at the register 0 or the accumulator. Okay. Excuse me. Now there is a configuration that wasn't included here. So supposed to be uh, since we're now at the program counter 20, so it should execute this halt. So according to our instruction set, upon executing this halt, the program counter will be set to 0. So once the program counter is set to 0, the random machine Turing machine, the random access Turing machine will be in a halt state now. Okay, so there should be an additional configuration right here. 0, 15, 0, 20, 0, 15, and empty set. Yeah, so let us proceed with the next topic, which is random access memory program abbreviations. So we can avoid the cumbersome appearance of random access machine programs by adopting some useful abbreviations. Okay. So for example, denoting the value stored in register 1 by R1, and then in register 2 by R2, and so on. So we can write this, no, as abbreviation of the following sequence. So rather than writing this, as mentioned, it is a cumbersome program, no, you could just write it down into a single line like this one. So this right here, this random access program right here can be abbreviated into shorter to this expression right here. And also, no, once we adapted this kind of abbreviation, we could use better looking names for the quantities stored at registers 1 and 2 and express the sequence of instructions simply as this one. So basically we can, to as mentioned right here, not rather than using R1, R2, we can just replace it with just variables like X to represent the register 1, and then the Y to for the alternative name for the register 2 or R2. Then also we can even use abbreviations like this one, no? While loop. So while X is greater than 0, we do this one. Okay, so this is the abbreviation for, let's say, X denotes the value of register 1. So this is the abbreviation for this program. Okay, so basically what this program does is just go into a loops, no? Because of this jump one, no? And as long as the this condition is uh, true, it will just keep on executing this one. So I think you're already familiar with this one. This is in higher level programming language. No, we could do that abbreviation to. We could write this program into this abbreviation. Okay. Then here's a much more readable abbreviation of the multiplication program a while ago, where Y stands for the register 1, X for the register 2, Z for register 3, and W for register 4. So just to read shortly, W, this is the R4. R4 would be equal to 0, and then while the value of the R1, register 1, is greater than 0, we'll just execute this one. So Z would be equal to the half of the Y, or the Z is the R3, Y is the R1. So by dividing the value of 1 by half, no, so we assign that value to the R3, and then so on and so forth. And yeah, once we reach the end state, once this one is no longer true, this condition, we will go into a halt. uh, we will execute this halt instruction, and therefore the RAM will be in a halt state. Okay, so this is what we call the sequential form of the RAM program. Excuse me. Okay. Also, this is also a sequential form also, but the difference is this is the abbreviated version of these programs. Okay, so this all of these, just to recap. Okay, this one right here, this is a sequential form of our RAM program, as well as this one and this one. These are all sequential forms of the RAM program. Now we could write or convert this into a flowchart form. So if you're familiar with the flowchart symbols, so we could do something like this, where we assign the start and stop, and then we, for this symbol here, parallelogram, this is for the input and output. The rectangle is for the process, and then the diamond to represent a condition, okay, in which it would the evaluation of this expression would lead to either true or false. So yeah, I guess you're for those who are familiar with the flowcharts, it's just easy to interpret this one. So just to by the way, this one here is just the flowchart version of this program here. Okay. Okay, so if we're going to trace this flowchart, so of course we'll start here, and then we read the x and y. After that, we assign w and z with the values 0, and then we go into this condition where if y is in this expression here, y is greater than 0. If this expression is true, we will jump right here, but if it's false, our program will stop now. So let's say if this is true, so we'll go here and execute this process. Then we proceed into this condition, a decision rather. Decision, yeah, this is decision, not condition. And what's inside in this decision here is our expression, which it will evaluate into true or false. So if it's true, if this is true, we'll execute this. This process here will run, and then followed by this one. But if it's false, so we'll just go straight into this process, skipping this one. And then right after executing this, or this process, so it jumps back again to this condition, this decision, and then yeah, the process just loops. So if it's true, of course it will go back again here. Okay, as long as the condition is true, we'll just end up in the loop, no? Until such time that this condition, or this expression y greater than 0 is no longer true, so our program will now stop. So yeah, I guess that's all for our topic, which is about Turing machines. And for our reference, so here are the references that we've used. So this is for the video from YouTube, and the other books, the other references are from PDF books. So yeah, thank you everyone for listening for our uh, video report about Turing machines, and bye bye and have a nice day.